Okay, in this video I just want to do a short introduction of Lesson 10, which introduces the concept of insurance. So hopefully some of this notation will be familiar and you'll recall some of these things from interest theory, right? So I'm just reminding you that the notation we used in there, that I is your effective rate of interest and D is your effective rate of discount, and the relationships that we know, for example, D is I over 1 plus I, and V, the discount factor, is 1 over 1 plus I, and V is equal to 1 minus D, and IV equals D. Delta, you recall, is the symbol we use for the force of interest, and that's related to I by the equation delta equals natural log of 1 plus I, which means that e to the delta is 1 plus I, and e to the minus delta is V. V to the t equals e to the minus delta t. And then we have these symbols for present values of annuities. So AN is the present value of an annuity that pays $1 at the end of each year for N years. And if you put the double dot, that means the payments are at the beginning of the year. And if you put a bar over it, it means the payments are continuous throughout the year. And if you have a superscript of M, it means that the payments are M times a year. So for example, an AN with a 4 as a superscript means that the payments are 25 cents at the end of each quarter for N years. Okay. So what we're interested in talking about here is life insurance. So we want to compute the present value of a life insurance benefit that's payable to someone at the time of their death. So the difference here is that we don't know when the person is going to die. So whereas in interest theory you always knew exactly when these payments were going to occur, here you don't. And so the present value is really a random variable. And what we're interested in computing is the expected value of the random variable. Okay. So we'll use Z in general to denote the random variable that's the present value of the insurance payment. Okay. Now usually insurance payments are made at or shortly after death, but in this lesson we'll assume that the payment is going to occur at the end of the year of death. That will make the time of the payment a discrete random variable, and that's a little easier to work with at first. We'll talk about the continuous case later on. Okay, so here's just a quick example to illustrate some of these ideas. So you're given this mortality table about probabilities of deaths for this insured person who is selected at age 70. And we draw a timeline here. And so right now he's 70 years old. And the time frame for this problem is 3 years, so we'll put 70 plus 1. And then since it's a 2-year select an ultimate table, we don't need the brackets after 2 years, so 72 and 73. And the insurance here pays $1,000 at the end of the year if he dies after 1 year, but not after 3 years. So in other words, if he dies in here between ages 71 and 72, he's going to get $1,000, or the beneficiary will, at the end of that year. Or if he dies between ages 72 and 73, he'll get $1,000 at the end of that year, and otherwise he doesn't get anything. So our present value random variable Z what are the possible values of Z? Well, it depends on when the person dies, right? So if he dies between 71 and 72, then the payment will be at age 72, and so the present value is going to be 1,000 V squared. And we're given a rate of interest of 4%, so we can compute this quantity, and it turns out to be 924 in some sense, so 0.556. And what's the probability that the present value is that? Well, it's a probability that he dies between ages 71 and 72. So that probability, according to our table, would be the probability that he survives to age 71 and then dies in the next year, which is 0.07. Right, so we're just using these probabilities right here from the table. And if you work that out, it's 0.0665. Yeah. 0.0665. All right. The other possibility is that he dies between age 72 and 73. In that case, the payment occurs at 3 years from now, and so the present value is 1,000 V cubed. And again, we can compute that. That's 888,996. And the probability that that happens, so these are the probabilities, is the probability that he survives the first year and the second year, and then dies in the next year. Right? So that's 0.08835. Right? So that's using these three probabilities. Right. And I guess we could say 0 is the other possible value of z, and that occurs with probability 1 minus the 2 probabilities that we just computed. All right, so I want the expected value of z. It's just a simple discrete random variables with 3 possible values, so we just do the weighted average of the values. So 924 times 0.0665 plus 888 times 0.08835, and let's see, that's 140. And that would be my expected value. Okay, so that's what I'd need to have today per insured if I knew I could earn 4% on my money, and I expected people to die according to this mortality table. We'll do one more example to illustrate the computation of the variance. So in this example, we're going to use the same mortality table as in the previous one. We've got this person who's 70 years old. Let's see, so 71 plus 1, 72. Okay. And this insurance pays a benefit of 1,000 at the end of the year if death occurs in the first year. So, well, let's see. Well, if he dies here, he gets 1,000 there, and if he dies here, he gets 2,000 at the end of the year, and otherwise he doesn't get anything. Okay, so again, Z has 3 possible values, either 1,000 V if he dies between age 70 and age 71, and that probability according to our table is 0.05, and 1,000 V is 961.54. We're using the same interest rate, 4%, as before. And then 2,000 V squared, which is 18, 19, 11. If he survives the first year but dies in the second year. And otherwise it's 0, right? So, same thing as before, the expected value of Z is 961.54 times 0.05 plus 1819.11 times 0.0665 plus 0. And that turns out to be 171.0428. And now, since we want the variance, we need the expected value of Z squared as well. So that's going to be 961.54 squared times 0.05 plus 1819.11 squared times 0.0665. You work that out, and it's 273,605. And then we can compute our variance using our usual formula. So 273,605 minus 171.0428 squared. And that works out to be 244,350. 0.086, and so that would be the variance. Now we're going to be talking about different types of insurance products, and we mentioned some of these in the Excel class if you took that. So, and we have a bunch of notation for the present value of payments under these different types of insurance products. So the simplest type of insurance is a whole life insurance that's just going to pay you $1 or some other amount at the end of the year of death, no matter when you die. Right? So if today you're X years old, then the present value, the present value random variable Z is V to the kx plus 1. Remember, kx is the number of whole years you've lived, right? So if you're age X here at time 0, and say you live 3 additional years and die in the 4th year, then kx would be 3, but the payment would occur at time 4, at the end of that year. So that's why we have kx plus 1 for the time of the payment. The present value of Z, in this case, is denoted by A sub x. So all of these use a capital A, and you can tell what type of insurance product it is by looking at the decorations around A, so subscripts, superscripts, prefixes, etc. So the next type of insurance is an N-year term life insurance. So that pays $1 at the end of the year of death if death occurs during the first N years, but after N years it pays nothing, right? So Z is V to the kx plus 1 as long as k sub x is less than n, but otherwise it's 0. And the present value random variable for that insurance is denoted by that symbol. So the n with the half box around it tells you the term, and the 1 over the x tells you that you get paid only if you die before n. So the time of the payment is is when you die, so that's why the 1 goes over the X. And you'll notice in this one, the 1 goes over the N. That is just telling you that the time of the payment is going to be at time N. So let's do that one next. The N-year pure endowment pays you nothing if you die before N years, and it pays you 1 at time N if you survive N years. So Z is 0 if Kx is less than N, and it's V to the N if Kx is greater than or equal to N. So we have 2 symbols for the pure endowment. So NEX is another symbol for it, and when we look at doing problems with the illustrative life table, you'll notice that some of the columns on that table have the heading NEX for different values of N. Okay, then you have an N-year deferred insurance, which pays you nothing if you die within the next N years, but pays you $1 at the end of the year of death if you die after N years. So Z is going to be 0 if Kx is less than N. It's going to be V to the Kx plus 1 if Kx is greater than or equal to N. Okay. So that's the symbol for a deferred, so with a slash after the N, or vertical line. And then an N-year deferred M-year term insurance, and I've got a slight mistake here, so this should be an N. Okay. So the N, it tells you how many years you're deferring, and the M tells you the time of the term. So if it's deferred 3 years, if N is 3 and M is 5, you get nothing if you die in the next 3 years. You get $1 at the end of the year of death if you die between 3 and 8 years from now, and you get 0 if you die more than 8 years from now. Okay. And then finally, the N-year endowment is a combination of the term and a pure endowment. So if you die within the first N years, you get $1 at the end of the year of death, and if you survive N years, you also get $1 at time N. Okay. And so for that one, we also have this symbol with the XN, but now you get both the payment at death if it happens before time N, and the payment at time N if you happen to survive. Okay. All right. One last thing I'll mention is, again, some more notation. So we know that the present value random variable, say for whole life insurance, is V to the Kx plus 1. Since V is e to the minus delta, we can write that as e to the minus delta times Kx plus 1. And therefore, if I raise z to the k, that's just going to be e to the minus k delta times Kx plus 1. So the difference between z and z to the k is just that I replace delta by k times delta. So if I'm going to compute the variance, for example, I'm going to need the expected value of z squared, and the way I compute the expected value of z squared is I do the same thing as I do to compute the expected value of z, but I use 2 delta instead of delta for my interest assumption. So we have a special symbol for that. K, a pre-superscript of k, means that it's whatever a we're computing, but with delta replaced by k delta. Right? So for example, if I want the variance of the present value of a whole life insurance, then I'm going to compute that as a 2ax minus an ax squared using our formula for the variance, and similarly for other insurances.